So the area I'm going to talk in this section is robot perception and how we can use ROS to do several tasks related to robot perception. Let's first understand what robot perception actually is. Before moving on to robots, think of a human. When we interact with the environment, we have different kind of parts of our body like eyes, ears, nose, which would help us to get some understanding about the external environment that we are in. Similar to that, robots also need to get some understanding about the environment or the real world that it operates before executing its navigation as well as manipulation task. So that is known as robot perception. So to do that, as we humans use different parts of our body, robots use different sensors. So moving on to the next slide. There's something common in many robotic platforms, which is known as the action perception loop. When a robot interacts with the world, it first gets some data or some sensor inputs from the real world. So that's known as sensing as well as perception. And then there's a central computer or a processor which acts as the brain of humans, and it decides what its course of action would be. And then it has actuators like arms and motors which actually delivers the action. So it happens in a loop. So uh, from the real world it sends, and then it decides its action, and then it executes the action, and again it's sensing the environment. So that's it. That is known as the action perception loop. So you can see a robot similar to a human here. So if you analyze this robot, you can see there are different parts in that robot. So it has a core i7 processor, and it has a battery pack, it has some actuators. So the important thing about robot perception is the sensors. So it has many different sensors. So it has two fisheye cameras and a laser scanner and initial measurement unit, pressure sensor, torque sensor. So different kind of sensors. So in addition to that, many different robotic platforms can have LiDAR sensors, ultrasonic sensors, different kind of cameras, RGB sensors, and so on and so forth. So let's move on to some robot vision applications. So uh, as humans, we also do these applications. So but they come naturally, right? So if you see the environment with your eyes, your brain automatically detects the objects in the environment, right? So there can be trees, there can be houses, there can be many such object lights there. What we try to do here is to give the robots the ability to do those tasks, but it's not going to be easy like as with humans. So we have to develop algorithms to execute those tasks. So object recognition means labeling an image with the label. So it has only one object, the image, you give a label to that. Object detection means in the image you identify different objects. So in that image there are several persons, or there are cars. So you identify different objects. So if you take this image, there's a Coca-Cola can and a glass, I guess. So you identify that object and marks the boundary using a bounding box. That's known as object detection. So object tracking is moving one step forward. So not just identifying the object, but you analyze its path with time. So if you in a video, these persons move, right? So in frame to frame, you track where the object moves. Face recognition is another interesting application. So in that, you try to identify the person using the features of the face. So it's another common application. In pose estimation, you try to estimate the different poses of humans. So collision avoidance is a very popular thing in robotics, because as humans, we when we move, we don't go and hit objects, right? So same thing should happen with robotics, because when they work with industrial or any other environments, it should it should sorry, I think I have turned off I didn't turn on my video. So in robotics also, they should avoid collisions. For that, they use different algorithms. So the last part is robot navigation. In robot navigation, they use inputs from the sensors to execute navigational tasks such as line following. In the next slide, we have a very common application, like a very interesting application talked in the last decade, which is self-driving. In a self-driving car, the environment is quite complex, right? Because when you move in a road, there can be pedestrian, there can be other vehicles, there can be static objects. So you should carefully decide your path without hitting anything, and even uh, even you should consider the regulations such as traffic lights and all. So perception is very complex in such kind of environment. So you use different different kind of sensors to achieve that. So there's uh, lidar. There are some cameras. There's an ultrasonic sensor, odometry sensors, radar sensors, as well as a central computer to process all those all those sensor inputs. So a LiDAR is a laser detection and ranging. So it actually scans the environment and build a point cloud map. I'm sure most of you have heard about these two terms, which are machine learning and deep learning. So in machine learning and deep learning, what you do is rather than using conventional algorithms, you build a network which consists of nodes, and you try to make the network learn to do something. So in conventional algorithms, we decide what the algorithm should be. We step by step tell what the algorithm should do. But in machine learning as well as deep learning, we give the network a set of inputs as well as uh, a set of labeled outputs. So the network itself learns what should be the what should it should do. So that's called as learning. So in machine learning, we manually extract features and give the features to the network, and the it can after learning, it can give the predict the output for a given set of inputs without after training. In deep learning, we include the feature extraction part into the network. So feature extraction and the classification algorithm all are done in a single network. These are some packages and frameworks used for executing computation as well as deep learning tasks. So OpenCV is a very popular package which can be used to perform a very a vast area of computer vision and image processing based algorithms, such as filtering, feature extraction, video processing applications, as well as some machine learning algorithms. So PyTorch, Caffe, TensorFlow, and Keras, they are all deep learning environments. So they can be useful in developing, training, and inferencing deep learning models. So let's now see how robot perception can be done with ROS. In the last slide, we talked about some technologies. So the interesting thing about ROS is we can use all those frameworks as well as packages with ROS. So ROS has inbuilt support with OpenCV through this Vision OpenCV ROS package. So you can directly do those image processing and computation algorithms inside ROS. And the deep learning platforms that I talked about, TensorFlow, Keras, and PyTorch are built on Python, and Cafe is a C++ based deep learning framework. So ROS has support with Python and C++. So we can easily integrate these deep learning frameworks with ROS and perform robot vision applications in real time. The other important thing to note down is the different sensors used for perception, such as cameras, lidars, has built-in support with ROS because they have specialized ROS packages. So those ROS packages are helpful to obtain sensor data using ROS topics using specialized ROS message types. So you can develop a perception system very easily with ROS because the all kind of many sensors already has the built-in support with ROS. So let's move on to some examples done perception examples done to ROS. So this is a pick and place robot. This robot has to identify the objects in front of it and put it into the correct container. For that, it uses a RGBD sensor. So the algorithm consists of two phases. So in the training phase, it collects information about the objects. So that from that image, that data, it extract hog and surface normal features. So features of an object can be like edges, corners and stuff. So these are some advanced features, hog and surface normal features. So based on these features, we train a SVM classifier. So support vector machine, also known as SVM, is a popular machine learning based algorithm. So we train that, and in inference, you get the point cloud data using the RGBD sensor, and we perform some pre-processing algorithms such as downsampling, filtering, and clustering, and then from the resultant image, we again extract hog and surface normal features, and then we input those features to the SVM classifier. So since the SVM classifier is trained previously, now it can detect the class of the object. So after detecting the class of the object, it can actually use its arms to pick and put the object to the correct container. So the next application I'm going to talk about is related with deep reinforcement learning. So reinforcement learning is again a popular area. So some of you might have heard that these reinforcement learning based algorithms have been able to outperform humans in certain games such as Go. It is kind of a game similar to chess. So the idea of reinforcement learning is you learn by doing. So you do different kind of trials, and you identify what are the best moves are. So from that, it learns by doing. So after training for a long time, it actually becomes better and better, and it has been able to outperform humans in some games such as Go and Dota. So in this particular application, deep reinforcement learning is used to train a robotic arm. So the objective of the robotic arm is to pick object precisely. So in the earlier runs, it is not able to pick the object correctly, but after some time, it trains, and it gets the ability of picking the object precisely towards the end. So let's look at some videos as well. So uh, yeah, so in this application, it's a, object recognition application. Uh, so uh, So in this video, what they do is they obtain the front view of the Coca-Cola can using a camera. Then it tries to extract features of the object. So features can be like edges, corners, and blobs. So after after identifying its features, so it uses a template. So yeah, this is the template image that they use. So in the template image also the features are present, right? So those features can be matched. So the template and the original image can be mapped. So the feature mapping would help to identify the object in the image. So the object can be identified using a bounding box. So in the next video, it's a face recognition example. So here also there's a robot, and in front of the robot there are three humans, which are actually not humans but simulations. But so you can see the persons are identified and faces are labeled with their name. So it again uses the features of the image for the algorithm to identify the person with its name. The last two videos are taken from the construct sim. So construct sim is a very helpful website which you can use to get a very good understanding about ROS. These applications you can try on your own by taking this course on robot perception in the construct sim. So that actually brings us to the end of my part on robot perception. So uh, it's time to answer some questions. So not just based on robot perception, but robot theory, robot perception, as well as the morning session. You can ask your questions on the same uh, Slido link, and we'll be happy to answer. Yeah, the first question is about what is LiDAR. So LiDAR is a very useful sensing sensor that is used in a vast number of applications. So LiDAR stands for laser detection and ranging. It's a device that emits a laser beam and it rotates. So the laser beam is rotated around the sensor. So that can be the laser beam when it hits a object, it would reflect back, and the reflection is identified by using the time that it takes to travel. You can identify the distance to the object, right? So that LiDAR can be used to actually obtain a point cloud. So the point cloud means the surrounding objects around the LiDAR with its distance data. I think Kitwin can answer the second
Maybe
question.
I will
Oh,
answer the second question. So, what are the advantages of SolidWorks over 3D Max? Now, honestly speaking, we have been actually using SolidWorks most of the time, and we have not really exposed to a 3D as 3ds Max, but I believe they are equally powerful software. But what you have to actually note is that all these softwares can export your robotic model in various common formats, right? So you can have like STL formats or DAE formats. So once you can export it, then in the Gazebo simulator or in the ROS framework, we can actually import. Uh, the ROS actually supports most of these common 3D formats, right? So whatever the 3D software, because we are not really relying on SolidWorks or any 3D software. It is just for that building or building the robot description part, right? So once we develop it, we can actually import it to our simulation framework. Then we can use Gazebo or some simulator, and then we are on the ROS side. Okay, so maybe I did not really answer your question because of my like I don't have much experience in 3ds Max, but I think that can be a reasonable answer for your question. So mostly SolidWorks is the one that we have been using to actually model the robots.
So I will answer the next on deep learning. How much time will it take for a beginner to learn deep learning together with ROS? The deep learning and ROS are actually two different parts, but they can be integrated. So when you try to learn, I think it's better to learn the basics of deep learning separately, as well as basics with ROS separately. So then when you obtain a good understanding about both those areas, then you can integrate to perform deep learning within ROS. So if I recommend you some material on this, so for ROS, you can actually use this ROS Wikipedia as a separate site, ROS Wiki tutorials, as well as the construct sims. They have a very helpful courses. And for deep learning, you have there are many courses. Actually, deep learning is a very popular field. So I would recommend some courses done by Stanford University and on Coursera. So even you don't have to take courses for both of them, because there are many materials available to study both of those areas. So you can actually self-study as well.
There's a question on whether we can suggest some resources for complete noises, and I would like to share that in the chat. There's this link, Getting Started with ROS. It's also actually written by Oshada and Sakuna, one two of our presenters. And please go through that, and you can find some nice resources on how to get started with ROS, and a lot of internet courses, open source courses. And I think it will be helpful for you. Dr. Pesher, you can take the next.
Yes, so the next question we have is in University of Moratuwa, what degrees are important to learn about robotics? What about mechatronics? Well, now robotics has become a very hot topic over like across departments. So as I told you earlier, it is multidisciplinary. So even though we don't have a department called robotics engineering department, like few departments, like number of departments in the university actually are really focusing on robotics applications. So we electronics and telecommunication, we do robotics in our curriculum. Then in computer science, they also have a separate section for robotics, electrical engineering, mechanical engineering. So likewise, actually that will also give you an idea. So these departments actually focus on different areas of robotics, right? So even though it's robotics, so we at our department, we focus on mostly the electronics part, and also that kind of thing. So in when it comes to mechanical engineering, they are more like focused on developing the mechanical structure and novel, let's say, legged robot mechanism, that kind of thing. So in the computer department, it's like they are more mainly focused on, let's say, learning algorithms or algorithm aspect. So likewise, so here it says, what about mechatronics? Yes, mechatronics, I think, is the best combination when it comes to robotics that you can have, because that really is a very close, that has a very close relation to robotics, because if you know mechatronics, you have a very high chance of succeeding in the, but that does not really stop you, even though whatever the field or area you belong to. I would say, since it's a multidisciplinary field, there are many ways to get your hands on the field of robotics. Yes.
So I will take the next question. Is there any specific reason to use the online platform that actually I think I mentioned? It's called ROS Development Studio, and we'll be doing a hands-on session with that platform. And I would say as Dr. Peshala mentioned in the earlier slides, installing ROS has a number of steps, and you have to do everything correctly, and it has to be done on Ubuntu. It's a somewhat tough process sometimes to get it running correctly. So the advantage here is on the ROS Development Studio, you can get a ROS project or ROS project running straightforward very easily. And that's what we are going to introduce you at the session today, and the hands-on session. Usha then Sakuna presenting the first session, and you can actually experience this for yourself if all of you stay for that session. And I would like to remind everyone who stays gets a certificate if you stay for the entire hands-on session until 5 p.m. Yes, so you can understand that question that as well.
Yeah, if I may add something, Kitmin,
Yes.
I think if we really ask, it would have been actually better if you could install Ubuntu in your machine and join this workshop. But here, as Kitmin said, there's some learning curve, and there can be some maybe problems for a beginner. And that's why we actually thought maybe it's really nice and easier to tell you what's happening in ROS on an online platform. So you don't need to actually install ROS when you participate in this workshop. So you just log in there and you do the stuff there. And once you get the understanding, leisurely, you can go to the ROS web page and follow the instruction and install, let's say, Ubuntu side by side in your Windows platform, and then install ROS as well. That's the reason why we chose the online platform. Otherwise, we will be having a very tough time answering Ubuntu related or other related questions if we ask you to come with a ROS installation. Yeah.
So the last question for this session is there any possibility to use the kinetic sensor in simulation and in the real world use the SIG sensor? So I believe this Kinect and SIG means different manufacturers of different sensors. So the advantage of using ROS is once you build the simulation, you can easily convert it into the real world later. So it doesn't matter whichever sensor you use in simulation as well as real world. So what's important is you give the sensor input to the processing part to the algorithms correctly using a ROS topic. So this Kinect sensor may be giving sense information in one format, and this it sensor might be giving the sense information is a different format. So you have to study their data sets and stuff. So I believe these two have ROS packages for these sensors. So the you can easily convert when you use ROS, because the algorithm or the processing part is actually independent of the sensors, as long as you obtain the sensor information correctly through the ROS topic.